Hello there. Been, what, almost a year? Probably. Today I'll be trying to show a bit of magic. A couple previous videos I was discussing about functions. What are functions? How eliminating a function is enough to describe computation. You can find those videos probably here, I think. To start, don't forget to like, subscribe, enable the notifications. Yeah, I think that's it. Today, everything that I do here will be explained better in a future video. But today it's, we're going to be playing. We're going to be just writing code that is probably going to be meaningless for you, but hopefully at some point it starts to work for you. I'm currently making a programming language. It's called Tikka. And Tikka is obviously the best language. The examples here are going to be in something very similar to Tikka. So if you want to know more about the progress about Tikka, I do live streams on Twitch almost every day. It's going to be coding Tikka, OCaml, Coq, sometimes Rust. And yeah, sometimes I do some game dev. Today there will be no type checker at first. We may have some type checker at the end of the day. The goal here is to internalize how substitution works and how it applies to essentially everything. First, let's imagine a very simple language. This language is going to be based on something called the calculus of construction, but it's going to be a degenerate version of the calculus of construction. First, let's define our language. Our language has a couple things. It has a type. We're going to get back to this. It has a for all, which is something like this. It also has a function, which is something like this. And it has a function application. Those make thesis formation for functions, introduction, and elimination. And this is very, very close to this system. Okay. One of the differences is that in this system, P is of type T. Here, P is going to be of type P. But you can see, here it's the for all, here it's the lambda, aka the function, application, and this is just like the language describing how to reduce. Let's start with a couple examples of how this language works. First, imagine that we had the booleans defined. You would be able to do a function from a boolean to a boolean like this. What is the type of this function? It's this to this. Notice, this is a function. I'm gonna put the parens again. This is a function. This is a type. So now we have a question. What is the type of this type? And the answer is that this has the type of type. And now we have a deeper question. What is the type of this? Everything has a type. The type of this is itself. This is called a very impredicative type universe. It has all sorts of problems. And also we have a missing rule here, which is, let's say we have a for all. We have a lambda and an argument. That's application. Let's say the type of the lambda is x of a to b, and the argument, so if that's the type of the lambda, the argument must be a. We're applying one to the other. What is going to be the type of the entire expression? You may be inclined to say b, but that's actually incomplete because x may appear inside of b. So the answer is b, where x was replaced by arg. And this can be seen here. This is the first rule. The way that we do it is like this. That's the second rule. You can see the type here, the type of b and l are the same. In general, the way that we say is that t is a type, t is also a type. So this is this. And here we say that a is a type, m has a type b, and so b is going to be a type. And we do that m, a to b. So that's the fourth rule here. This one is the rule for variables. Let's ignore it. And the application is this rule right here. So instead of lambda, he calls it m and n. And this is going to be m n x by n. That's this. Okay. This one is just the language saying, hey, there is some relationships, but we're going to be ignoring those. This is the type of everything. I'm going to keep it here. It's also important to understand how this reduction works, but you can think about this as all occurrences of x inside of b are going to be replaced by n. So if b is just x, then this is going to be n. If b is x plus x, then it's going to become n plus n, and so on. This language has everything. It has simple functions. Those are functions that accept terms and returns a term. So you may imagine something from an int to an int. That's an int to an int. It also has functions from types to types. You can imagine this as a type constructor. you know, you could do 2a. So that's a type constructor. I'm gonna leave it here. It also has functions from types to terms. Those are called polymorphic functions. You may be familiar with the identity function. So this accepts a type and returns a term. This is a term. And last but not least, we have functions from terms to types. So this is a function that, let's say, accepts a boolean, and it's gonna return a type here, where the boolean appears inside of the type. One example is, let's say that we had pattern matching. I could do match b. True is going to be int and false is going to be string. Okay. But this is an incomplete example. We're going to go back to this one. Those are 4 types of functions. Most languages, you may know this one. This one is also very common. It's also known as generics. This is parametric polymorphism. This is very common type constructors. This is not very common. Okay. And that's the interesting one. Another thing that I'm going to be adding is aliasing. Aliasing is going to be something like you can do x is equal to y in b. So what is this? Actually, this is the same as getting, well, I'm going to use m and n. If you get n and all the occurrences of x are going to be replaced by m. This is a let, but this is just sugar. Keep that in mind. This is not needed. It's just a way for us to avoid duplicating stuff. What can we do here? The answer is almost everything. It is actually true incomplete because of the typing type, but let's not look on that too much. First, we need a way of representing data because, you know, programs are about manipulating data. How do we represent data? It's by using something called church encoding. Church encoding essentially shows you how to internalize operations of data. First, I'm going to be focusing here mostly on the booleans because the booleans are a very simple bit of data. What is the most important thing that you may want to do on a boolean? It's an if. Okay. That's by far the most important thing that you can do with a boolean. So let's define an if, and our if is a function. It accepts a boolean. We call this boolean the predicate. Then it may be 2 options. So it may be here it's when it's true, if true. Here it's when it's false. And here it's the return. This requires you to do a bit of polymorphism to describe this type. Here we're going to be, if it is true, it's going to return this. So when true. We can call this then else a, and it's going to return an a. Let's not define this function. We cannot define this function because we do not have the booleans yet. So this is missing. How do we define the booleans? We define the booleans by internalize this notion. This is all the computing that the booleans provide. So we say that the booleans are equal to this. So this is the type of the booleans. I can give you examples of how this could work. So let's imagine true. It's going to accept a, then else. If it is true, it returns then. If it is false, then else. Notice that I did not put the types explicitly here. You can try this in TypeScript if you want. This is going to work because it's going to look at the type here and propagate. It's a kind of inference. It's a weak form of inference. How does this work? This works because if I do true, and let's say it's going to return another boolean. I do true. It's going to return true. Here, it's going to return false. If it is true, it returns true. How can I know that? Because if I do this, I can go here and let's expand this a bit. I'm going to actually annotate so that you can see what I'm talking about. But I'm just going to annotate the true. So I set this, which is going to be the same as this. I find all occurrences of a and I replace it by bool. Nice. So now this accepts a boolean. This is polymorphism, but now we are going to go then, same stuff, true, erase the parameter, erase the argument, false, again, it does not occur. So this is equal to true. What if I do false? We're going to go to the same process, but we can go a bit faster because the types are not there. So erase it, true is not there, erase it, false, else, false. So those expressions are the same, just by beta reduction. This is this rule right here. This is the 6th rule. It's a very important rule, but it allows for us to do a couple interesting things. First, it allows us to do computing, but because we have data I can do something interesting. Here I'm using this function, right? Which is here it's this, which is a polymorphic function. Then I'm using simple functions. I'm not going to be using type constructors that much, but we are going to see a bit of them at the end. What I'm also going to be using here to show why is this function interesting is because now we have b. So I can do type, int, and string. And this is the same thing. What does that mean is if Boolean is true, this is going to be an int. Otherwise, this is going to be a string. Not a string. That's going to be the type int and the type string. Because this expression has the type int. To show this, let me do here. Let's see if it is true. I'm going to expand it. You know, a is type. Okay. We are saying that int is a type. We don't have them defined here, but let's imagine they are here. String does not, so here that's erased it then. And here I'm gonna erase the else. So if b is true, that's the case. And I can do the same if b is false. Type is not appearing because we do not have that notation, so it's easier. Int is also not appearing because that's false. String else appears, so we can erase it. And that's it. What does that allow us to do is to do computing at the type level. Not only at runtime, but we can compute arbitrarily compile time. One example that I find interesting, you can do this in TypeScript, which is let's imagine a function that takes a predicate. So it takes a Boolean. Oh, we can define this if function now easily. The pred is a Boolean, a then else, and this is just going to be pred, a then else. But that's not an interesting function. So one function that I find interesting that a lot of people when starting to code in type languages, they wonder about this is how do I do a function that if something is true, it expects, let's say, an integer. If it is false, it expects a string. Here my examples are going to be bool and net. Here I can do it. I can do it by doing pred, type. If it is true, I want it to be, let's say, int. Otherwise, it's going to be a string. And then it returns x. Let me show you how this works. First, let me expand the type of this function. The type of this function is pred, bool, x to this, okay? So that's the type of the function. Let me put the equal sign here. What happens when I call this function with true? So let's say I'm doing x, f of true. What I can imagine here is the same because of this rule. I get the type b, which is this. I can erase it here. And all occurrences of pred are replaced by n. So in this case, pred is replaced by true. And I'm going to simplify a bit, but you can see that true type int. So this is going to be an int. And this is also going to be an int. So this is true. The same happens if I try with y. Let me do a and b. If I try it with false, again, I get this. I put false here, and now I know that it's going to be string to string. This is a thing that it's very, very naive, but it's already quite cool. Because that allows you to compute on the type system and do simple stuff such as branching. Branching is one of the main missing things that you don't have on the type system. The other one is recursion. But by having the booleans and the naturals, because with the naturals you gain recursion, you can compute on your type system. This is the power of dependent types. Why? Why would you want this? You may be like, oh, this is quite complex. It's actually not, because that's just your traditional intuition works. But for me, the interesting thing here is from dependent types, our major win is that now we can do tests on the type level. We can actually compute on the type level. That allows us to do tests. Not only tests, it allows us to do a more fancy thing, which is called a proof, a mathematical proof. Tests and proofs are almost the same. It's just that in general, proofs are more powerful, because in general, tests, you're like trying one case, two case, three case, I don't know, 1,000 cases. With proofs, you can test infinite cases, which is way more powerful. Now, I'm gonna say something very deep. Something that you could probably spend years think of. I know because I did. I've been spending like almost 2 years at this point thinking about it. Types are propositions and terms are proofs. Let's repeat. Types are propositions and terms are proofs. What does that mean? That means that whenever I do something like this, whenever I say something like x, is of type bool. This is a proposition. What is this proposition saying? There exists a boolean. What is the proof of this proposition? True is one proof. False is another proof. This is not a very useful interpretation on the beginning, but it becomes super interesting when we introduce something else. Let's go a couple of simple functions again. One very interesting function, which is super simple, it's this function. If this is a proof, it should be a proof of a proposition, right? Which proposition? That's the same as asking what is the type of this function? X, bool to bool. How do you read this in plain English? You read this as assuming a boolean x, it returns a boolean. In a more mathy way of saying it, if a boolean exists, then it implies the existence of a boolean. This is what this function is doing. We can make this more interesting. Remember that I was talking about tests. To write tests, we just need to imagine something. What is a test? A test is something that you have something on the left, something on the right, and you check if they are equal or not. To do this, first you need to be able to define equality. Because, you know, we can already have two things. I could do x of boolean, y of boolean. But I need to be able to define equality. How do I define equality? Equality, it's going to be defined by Leibniz equality, which essentially says that two things are equal if for all propositions, those things are equal. So if it holds for px, it holds for py. P being a proposition. How can we write this proposition? The proposition of Leibniz equality. First, let's imagine we need a proposition, okay? And here it's something that returns a type. And what we want to say is, if it holds for px, this is just the same as doing. So like those things are the same. It's just that it's more natural to write like this. So if it holds for px, if you give me a px, I give you a py. There's a couple of problems. This is missing. There is no a, no x, and y. The solution, here I'm going to be using a bit of Sugar's syntax. Mostly, a is a type. Okay. X is a, and y is a. Keep in mind, this is the same as doing like, you know, that's the same as doing type x of a, y of a. And notice that here I'm using, here it's a lambda, it's a function, and here it's a type. Because here I'm using this. So this is a function that returns a type. A function that takes an a, which may be a boolean, for example, and returns a type. That's a dependent type. We also have here type constructors. Oh, this is also a dependent function now that I think about it. Because it accepts a and returns a type. And this is just very common when you're doing dependent types. Actually, this is also a type constructor, because it takes a and eventually it's going to return a type. That difference between type to type, term to term, type to term, and term to type kind of disappears when you actually have the calculus of construction. So this is the equality. Now we need something of this type, because we are saying that equality, we are stating the proposition of the equality. This is not a proof that equality exists. The proof that equality exists is what we call reflexivity. Reflexivity is like, for equality, it just says that, you know, there is an a, x is equal to x. X is always equals to x. That's the law of identity. Very important. And so here, I need to accept those parameters. A is going to be a type, x a, y a. And here, I can do the same. P is going to be a to type. But notice, because I'm saying that this is x, so here it's going to be px, but y is also x. So I just return p. And that is a proof of the equality. Why is that interesting? Because in general, when we are doing proofs on type theory, we are always talking about equalities. It's reasoning about equalities. There is a book, if I recall correctly, about this. This is reflexivity, but I'm going to use riffle. How does this allow you to write tests? You may be wondering. Let's try to write a very simple test. A test that I think it's the degenerate test. It's that the boolean true is equal to true. How do I do this? Riffle. Bool. Oh, sorry. There is no y here. True. And, you know, we know this is equality. Why does this hold? Because riffle has that type, right? If boolean is here, I know that it's going to be x and x. So this is true and true. And this is the same. Okay, so this is the same. Let me show another example. I can do the opposite, right? With false. And how does that work? Why is this the type? Let's get here. What is the type of riffle? Riffle has the type this to this. Okay, so that would be the type. I passed boolean, so A becomes bool. I pass false, so X becomes false. That's it. This is, you may be like, oh, yeah, sure, that's not very interesting. So let's define something deeper, a more, maybe slightly more concrete case. How do we do using booleans? How do we do the NOT gate? The NOT gate is very simple. B, it's going to return a boolean. If it is true, it returns false. If it is false, it returns true. What you may want to prove of this? You may want to say that not true is equal to false. How do you do that? What do you put here? Notice that I was already able to write a proposition. How do I show this? I can show this by reflexivity. I can literally be like, riffle, bool, false. And that's going to work. Why is it going to work? Because it's going to get this and it's going to compute on the type system. So we are going to first expand not. Okay. And so we know that B is true. And we know that true always returns the first value, which is false. So this is the same as this. Actually, I could do like not true here easily. It would also work. Those two are the same. And here I was able to show that not true is equal to false. Can I do the opposite? Yeah. Not false. It's going to get to not. B is going to be false. False is going to return true. True. Riffle, bool, true, true. So this is a proof. This is also a test. In fact, we can do more stuff, but this is a very, very simple test. In your traditional language, if we had a type checker, this would fail to type check. Why is this important? Because here I'm running at compile time and I have a guarantee of the compiler that this is always the case to begin. Like I know that this holds, okay? No, like I know that not does not have a side effect. I know that it's always going to be the case. Let's go a bit deeper again, okay? Let's get more concrete. What is the advantage of this kind of test over traditional tests? You may be asking. First, anything may appear here. So you're able to prove stuff for any number of values, including infinity. I'm going to be moving to something called coq. Coq is a tree improver, and I can show everything here in coq in a slightly different way. Coq has the naturals already defined on the language. But what do I want to prove? First, I want to show you a simple thing. I want to show you that true is not equal to false. To do that, you need a thing called induction, which is what this system did not have. Well, it kind of does, but I'm not gonna get too much into the grainy details. How do I show that true is not equal to false? I can do true, false. And in coq, there is a couple ways of writing code. I'm going to be using eauto here. It doesn't work, sad. I can do unfold so that you can see here. This is the same as a function that if you give me true is equal to false, it returns false. But notice this is capital false. This is an absurd, okay? And that's how we define not equality. We define it by the principle of non-contradiction, which means if true is equal to false, you can prove anything. The easy way to do it, this is I introduce the equality. I can do discriminate, QED. This is a proof. We can call it a lemma to be fancy, that true is not equals to false. The simple examples that we were doing before, let's define not again. I can do B as a boolean. Now we have pattern matching, which makes our life easier to reason about. False, false, true, and so the example that I had before is not true is equal to false. How do I do this? I can have a lemma. Actually, I'm going to be using definition here. True, not true equals false. I go here, not true is equal to false. I can prove this by reflexivity, and it holds. What happens if I put true here? It fails. Cannot unify, not true, and true. Those are messages that are terrible, but that's a problem of coq. The same, not false is equal to true. So you can see that this holds. What is more interesting on all of this? All of this is strictly about substitution, and we can go further. Now let's play a bit with the naturals. Okay, coq already has defined addition. You can see here the definition of addition in coq. It's just a recursion. Not going to explain. One of the things that you can show in general is 0 plus 0 0 add 0 equals 0, right? Equals 0. That's reflexivity. It holds. 0 equals add 1 equals 1. That also holds. Let me try another number. 2. You got the idea. I can show that for infinity. Well, I could keep going by infinity. But the thing is, can I say inside of coq itself that 0 plus 0 at n is equal to n? The answer is yes, I can do. For all n being a natural, 0 plus n is equal to n. I need to put definition. Problems of coq. And here it should be n. Does this work? Yes, it does work. This is not the interesting one. This is very easy. How is coq doing? Coq is getting the definition of addition, expanding, trying it. And you can see here by the definition of addition, when it's 0, it returns m. That works. The problem is the opposite. The problem is n at 0 is equal to n. So I'm gonna reverse. And you may be like, oh yeah, sure, that also holds. That holds by commutativity, which is a very annoying property to prove. Not super annoying, but kind of annoying. Here we're gonna enter in proof mode. Proof mode is just a way of writing code without writing code. Actually, let me show you this. So this is just true, nec false. Okay, and this piece of code is generated by this. So at the end of the day, you're writing code. Just think about it as a macro system. When you try to do this, I can introduce n, and now I need to show this equality. What is the problem? If I unfold plus, you can see, yeah, it doesn't know what n is, so it gets stuck on the pattern matching. What I can do is do induction on n. Induction for the naturals is the traditional thing of like, if you show it for 0 and you show it for any number plus 1, you can show it for all the numbers. So here I have two cases, 0 plus 0. I can simple it and reflexivity, which by the way is the same as doing equal refl by returning. And here I have the inductive hypothesis. I'm gonna do simple. Now I have this. I can use the inductive hypothesis to rewrite. And again, this holds by reflexivity. And that's a QED for you. This is what coq allows you to do. This is not something that most languages can do, but this is the power of like generalizing the notion of substitution over and over and over. At first, we had the simple type lambda calculus, then we had the system F, then the system F omega, and at the end, we get the calculus of construction. All of those are useful on their own for many, many reasons. But when you combine all of them is when a language shines. I really wanted you all to understand this, to understand this notion of propositions, proofs, code being proofs, types being propositions. Those are super, super useful. And it mostly allows you to see the implications of programming being a form of algebra, right? The thing that I mentioned, I think on the video somewhere here, about like programming is about elementary algebra. If you keep applying this, you eventually arrive to this conclusion. To be fair, that is a lot of history. It took computer science many years. For comparison, the calculus of construction is from Tikka 88. We are talking less than what? I think it's 31 years if my math is not failing. So yeah, 31 years. That's really, really cool. Anyway, if you want to know more, follow me on YouTube, Twitch, Twitter, and that's it for today. We're gonna have more getting in details for each one of those topics. See you all in the future. Bye bye.